the client, who was very heavy into that design, who had done a lot of correlations, that he had the best correlations using the task program. On the PFR program, we use that for radiant complex heaters. We will basically put in the geometries of the radiant and convection sections. Then we will take in import process duties, and that will basically confirm that the heater is able to do the specified performance without overheating tubes or have process fluid degradation due to local hot spots in the tubes. We will use the PV Lite Code Calc program for mechanical checks of the exchanger design. ASME Section 8 now has a new code requirement for tube sheet design, which this program handles very nicely. That was used for some very large exchanger designs that we did for the North Slope. Compress will also do that, but that's we find that to be much more complex. And typically, if we get into compress, we'll ask for the support of the vessels group to assist us in that. So this is the equipment types that we'll cover. Various types of exchangers, fired heaters, heat recovery steam generators, waste heat recovery units, flares. So let's jump into shell and tube exchangers. I think that is sort of on our time frame. This is the basic equation we use for heat transfer in a shell and tube exchanger and other types of exchanger where we have heat transfer between two fluids or heat transfer to any fluid basically. This is the Fourier heat conduction equation, where heat transfer equation, where U is basically an overall heat transfer coefficient, A is the area, F is a correction factor, depending on the type of shell and tube configurations we have. And LMTD stands for the log mean temperature difference, which we'll cover in the subsequent slides. A little bit of background. This shows you the types of exchangers that are defined by TEMA. This is in your handout if this isn't too visible here. The more common types on the channel sides, these are basically channel components for either the inlet or the outlet, depending on the exchanger configuration. We have an A-type channel where we have a full bolted cover. B-type is where we have a bonnet type. The selection between these two is usually made by the client based on his desire to minimize the number of leaking flanges. This defines the type of tube passes we have. This is an E-shell. We can have single pass, multiple pass. It'll be a little bit clearer as we get to the subsequent slides. Again, this is the turnaround in over here where we would have a fluid flowing in, coming in the top nozzle, going through the exchanger, coming out here, turning it around, and then going back the other side. For your information, the typical convention is if a fluid is being cooled, it comes in the top, out the bottom nozzle. If it's being heated up, it flows in the bottom and out a top nozzle, just based on the change in the density of the fluid. Let's go on a little bit here further, it'll be a little bit clearer. Here's an example of an AES exchanger. This will be the channel. The tube sheet is the separating partition between the shell side and the tube side. It is a code design component. So in this case, if we're flowing into the channel, we would flow through the tubes into this. This is called a floating head. It has a mechanical split ring which basically holds the let's do it this way. It would hold this cover onto the floating tube sheet here, and basically that would allow the fluid flowing into the channel, through the tubes, down, turning around here, and then flowing out the outlet. That basically would define the tube side pressure boundaries for this type of an exchanger. With an S-type head, you would require to have a full diameter channel cover. Actually, it's larger than full diameter because you have to be able to pull the bundle. You have to take off the shell cover to access the floating head bolting here. This is an example of an AET type floating head. The only difference between that and the one that we saw, which we'll back up for a minute, this is now a full diameter floating head, and that if you want it, you would have the ability on a T-type head to actually pull the bundle. The shell diameter would be equal to the head cover diameter that's here. So if you wanted to, you could unbolt these flanges and you could extract the bundle from the shell, all in this, in the channel side. So you would pull it out in that direction. This is an exchanger that was used at Drill Site 1J to heat a heavy crude using a hot oil. Amy was lucky enough to go up there to assist in the startup of that facility. Here are some other types of exchangers. Let's see, which are some interesting ones. Let's see. This would be a BEM type exchanger. We'll cover this later. You can have many different options on that. You could, besides a bonnet head, you could also have a conical head, which would be like this side. You could actually have pure axial flow, where this bonnet head was actually a cone, so you would flow into the tube field through a conical head, out through the tubes, and then either exit with a concentric cone, which you have here, or you could potentially have an eccentric cone if you were condensing liquids. That way you would not trap liquids in the outlet channel. This is called a kettle type reboiler. K stands for kettle. You could have a BKU, an AKU. In this case, this is an AKT, but if you were to make this a U-bend tubes down here, get rid of the floating head, then that would be an AKU reboiler. As I was saying before, this is an example of actually this is a BKM unit. This was used for one of the low temperature separation facilities in Alaska. You can see this is the inlet nozzle here. It's a concentric cone. It was bringing in a two-phase liquid, a little bit of condensed gas, or condensed gas, and the balance would be the gas vapor. This had a little diffuser in here to ensure that when the two-phase flow entered the channel here, it was dispersed so that it effectively distributed the liquid and vapor into the tube field, which was right about at this point. You can see on the outlet side, this is an eccentric cone, so that as you dropped out more gas liquids, and that then went into a separation column. The liquid level here This utilized a liquefied propane, which would boil at minus 50 degrees Fahrenheit. A couple of interesting things about this: the vapor, the boiling vapor. These would be the suction lines going to a propane compressor, which would take the vaporized propane, compress it, run it through a set of condensers, just similar to a refrigeration system like on your car, where you compress it, cool it, and then expand it through an expansion valve to achieve the low temperature again and make the liquids. This unit used a proprietary tube called made by Union Carbide, called a high flux tube, that basically promoted nucleate boiling, so that it had a coating on the tube to promote localized boiling points to enhance the cooling of the gas by boiling up the propane liquid. This unit was built in Korea. Pardon me. This unit was built in Japan. It's an example of a TEMA data sheet. If you'll notice that in the back of the handout, I have included all of the typical heat transfer data sheets that we utilize, and you'll see that these are that this TEMA data sheet is very similar to the shell and tube data sheet that's included in the back of that package. This talks about the scope of TEMA. Since my eyes are going here, I need to refer to my hard copy here. Basically, the first half up here talks about the inside diameters up to 100 inches. It talks about design pressures up to 3,000 psi. It will define that typically on all of our petrochemical process work, we will use TEMA-R. There are two other types. There's TEMA-B and there's a TEMA-C. TEMA-B would probably be more applicable to a pharmaceutical type unit. TEMA-C is more applicable to a utility type exchanger. But for all of our process work, we apply TEMA-R, which basically imposes a 1/8 inch corrosion allowance on all of the corrodable areas that are identified by the material applications or the material sheet. Further down here, it talks about the construction codes. Typically, ASME code is applicable. Under material terms of conditions or definition of terms, all of the code materials that we utilize have to be listed in ASME code section 8 or section 1. We would utilize the allowable stresses that are indicated. In some cases where we have alloy exchangers, the alloy material may or may not have a corrosion allowance. If we have a clad vessel where we have carbon steel with an alloy clad, the alloy clad typically would have the 1/8 inch corrosion allowance applied to it. So once the clad material is identified, there is no additional corrosion allowance that's applied to it. Just about anything you want. You can carbon steel, Incoloys, Hastelloys. We just got into an issue on that, which there are many ways to apply a clad. You can either use a roll bond clad, or you can use an explosive bond clad. On explosion bonding, they will basically put the alloy sheet on top of a carbon steel plate. They will submerge it in water, or sometimes it will just be not submerged. They will put an explosive material on top of that, and they will detonate the explosive, and that will impart enough energy to the clad plate or to the alloy plate that will actually form a metallurgical bond to the substrate or the carbon steel plate. Roll bonding attempts to do that. It's a good way to do it, but if I do not have any photographs, but if you do a micrograph and chemically etch it, and then look at an explosively bonded clad plate, you will have a very the layer between the alloy and the carbon steel. You'll see a transition between the two materials, whereas on roll bond you'll see a much more defined fusion layer. So explosion bonding is a very, very good way to go. This shows the type of baffles that are available in shell and tube exchangers. They'll typically be selected based on the pressure drop and maximizing heat transfer considerations. This is a typical segmental baffle with a horizontal cut. Basically, the fluid flow will go up and down. We'll have a more detailed presentation of that. This would be a vertical cut where the fluid flow basically is going side by side. This is an angular cut. We haven't used those, and I'm not familiar with one that we've used. This is double segmental, where the flow basically goes back and forth, but the flow pattern, there's an intermediate baffle here, and this is typically used when you want to minimize pressure drop. Here's an example of a segmental baffle vertical cut, but it's a very special design because it's no tubes and window. You lose tube surface area, but you greatly reduce the risk of tube vibration because of your ability to put in intermediate support plates. This is a baffle here, baffle plate down here, another baffle plate down here. Now there'll also be a baffle plate with a full, like you show here, there'll be one on the opposite side midway between this baffle and this baffle here. What that does is that the first baffle, you'll be flowing across the bundle in this manner from right to left, and then the flow will proceed down the shell until it encounters the next baffle, or let's say there's a solid plate further down that will prevent flow in this area, and that will redirect the flow back across out of this section. It will turn around and then go back across and right in this area. This is an example of baffle plates for eight of these exchangers were fabricated, all with no tubes and window. This shows only partial tube out because this was pushed into a shell and then the tube sheet was put on the far end once the bundle had been inserted. So here's a baffle which shows the window closure here. These are segmental baffles or intermediate support plate baffles down here, which it basically allows you to reduce the unsupported span of the tube to minimize, again, cross flow, which is caused by vortex shedding of the flow as it goes across the tube. The longer the unsupported span, I don't know if you've ever encountered a flagpole in a wind. It's very interesting to see. You'll occasionally see that you'll have the flagpole will start to vibrate, and it'll have different node points depending on how it's vibrating. So the same thing can happen within a shell and tube exchanger, and what will happen there is that the tubes will actually vibrate to the point where they can collide with one another. That will cause cause erosion points where the tubes are colliding, and that will lead to tube failure. So to give you an idea of how big that unit was, this was fabricated in Korea for an upgrade of the North Slope low temperature separation plant. This talks about impingement protection for the exchangers. You do not want a process stream entering an exchanger that has the potential energy to cause the tubes to vibrate or to cause erosion. This is basically term is rho v squared, density times the velocity squared. 1500 is the typical limit, or where we would impose the installation of an impingement plate. What that does is that takes the energy of the incoming process stream and diverts it horizontally so that it enters the tube bundle with minimal potential for causing the tubes to vibrate. As part of the HTRI program, we have a vibration printout which will give us a potential warning for vibration. We check the nozzle velocity, nozzle rho v squared. We check the entry rho v squared. That's basically the distance under the nozzle to the impingement plate, and ensure that that is adequate so that we do not have any vibration. This kind of gives you an example of the Fourier heat conduction equation. These are the elements that go into that. U is basically made up of, for those that you have taken in the electrical classes, if you have a series of resistances, or let's say elements that are in series, it's the reciprocal of each of the individual resistances, the overall sum of those. So we take 1 divided by the resistances. This would be the inside tube resistance, which would be based on an inside heat transfer coefficient 1 over that coefficient. And the tube side coefficient is based on the Reynolds number, Prandtl number, etc., to come up with correlations based on the type of fluid that we're dealing with, and the HTRI correlation will basically give us what that inside tube coefficient is. We've specified a fouling resistance either by TEMA or by industry standards or client preference. Sometimes the client will elect to override a fouling factor to be conservative. Typical fouling factors for most of our streams, we use a 002 fouling resistance, which may not seem large, but if we have a very high heat transfer coefficient, that will significantly reduce the overall coefficient. Here we take an area ratio to basically convert all of the heat transfer coefficients to the outside tube surface area. This is tube metal resistance based on the type of tube that we elect. Stainless steels have a higher resistance than the carbon steels do, so there's a slight penalty for the alloys. Then we have the shell coefficient and a shell side fouling factor. Then this reflects this evaluation of this equation gives us an overall coefficient. Pardon me while I have some more water. Anybody want to break or continue here? Okay, let's do a quick 10 minutes.